All right, good morning, everybody, and welcome to the March edition of the Wikimedia Research Showcase. We're here in San Francisco on a rainy and sad day, but we're gonna warm your hearts with some amazing research. And we have a crowded room here. There are some special guests. We have Robert West from EPFL, and we have Michele Catasta from Stanford. And of course, the rest of the crew here. And I'm delighted to have to do today two presentations that are really part of a major program that the Wikimedia Foundation research team has been conducting in collaboration with a number of institutions, including EPFL and Stanford. And we have Tiziano Picardi with EPFL is going to give a first presentation today. About methodological challenges in the use of the category network in Wikipedia to extract some meaningful relations. And this is going to be followed by a presentation by our own Diego, who is going to present the second part of this work about section alignment across languages in Wikipedia. All of this is part of a major program that we're investing into with these partner institutions to try to understand how to design recommender systems for article expansion. So I'm really excited to have you here. As usual, some house rules. The presentation is going to be broken down into two parts, 25 minutes, followed by a short Q&A. Please stick around at the end of the showcase. We're going to have, as usual, our final open discussion at the end of the two presentations. Miriam Reddy, who's here on the Hangout, is going to be our host on IRC. So if you're following the discussion on the IRC channel, Wikimedia Research, please ping her with your question and she will relay them to the room. So with that, I think we're ready to get started. And Tiziano, the stage is yours.
Okay, share the screen. Okay, hi everyone. And thank you for the opportunity of presenting today this research. This is, as Darius said, is part of a larger project about sections recommendations. I work on this project with Michele Catasta from Stanford University, Bob West, my supervisor in EPFL, and Leila of Wikimedia Foundation. Today, we are going to talk about taxonomies, and in particular, how to clean the category network to extract a taxonomic structure from the categories. Let's start with the definition of taxonomy. Taxonomy is an hierarchical organization of concepts. Typically, they are these entities are linked with is a relation. Like in this case, we have a small example of taxonomy where we have animals, mammals, felines, and you can see there is a relation between felines and mammals and animals. This is a very intuitive and natural way to organize a concept and to reason to model the world. In the taxonomy terminology, typically people use the term hypernym and hyponym to define hypernym, a parent of a concept, and hyponyms, the set of children. So animals is an hypernym of mammals, for example, in this case. And taxonomies are useful in many different domains. For example, in image classification, people use taxonomy to, for example, in satellite images, to bind a different level of zoom to different level in the hierarchy of the taxonomy. So a forest could be labeled as a green area in a different level of zoom. Another typical context is the medical domain, where people can model diseases and symptoms in a hierarchical structure and can run on top of this automated reasoning tool to find the similarity between concepts and to generate a new knowledge. Another application could be question and answering bot. So a program can infer new knowledge from the model and answer a question about an entity that is not explicit in the model. Let's see an example to make this clearer. Again, we have the small taxonomy about animals. And in the example labeled as number 1, we can, by following this transitive is-a relation, infer that a feline is an animal. Even if this is not explicit in the model, you can just follow the path of is-a relation and infer this new knowledge, not explicit. A second example related to the question and answering bot is the number 2, the example labeled as number 2. We have a statement that all animals must eat to live, and this is a property in the top level entity, animals, as you can see on the left. And if we have a question for the bot, like does Garfield have to eat? The bot can check that Garfield is an instance of a domestic cat, and by following this path of is-a relation, can infer the answer to the question, even if, again, this is not explicit in the model. But we are interested in Wikipedia, and one good and nice application of taxonomies is the sections recommendation. Leila presented this problem in the showcase of December, but to give you an intuition, basically we are developing a recommender system to provide recommendation to the editors about possible missing section in the article. This is the interface we envision for next generation of the Wikipedia editor. In this case, basically, we want to generate a recommendation based on the concept. So if it's a biography, we want to extract a set of sections relevant for a biography. Let's see in practice how this can work. In this example, we have people, scientists, and actors. Scientists and actors are children of people, and scientists and actors have a set of frequent sections that in particular are early life, personal life, and death. And for the specialization scientists, we have a word. For actors, we have filmology. But if we go up and we search for common structure, we can generate a template composed by early life, personal life, and death that are representative for the biography of people in general. The problem with this is it's a nice application, but generating a complete taxonomy manually is not feasible, because in Wikipedia we have many languages and potentially thousands and thousands of concepts. So we should find a way to automate this task. But the good news is we have a category network. So I'm sure you are familiar with the concept of category in Wikipedia, but let's see an example. In this case, we have the page of Claude Picasso, the son of Pablo. And at the bottom of the page, there is a list of categories assigned to this article. In this case, we have a French artist, French photographer, French photojournalist. If we click on a French artist, we can see the details of this category, and we have subcategories and parent categories. Is potentially we can see this as a set of hyponyms of the entity French artist and hypernyms for the parent categories. This is it's very tempting to use this category network to generate a taxonomy. Unfortunately, it's not so easy, and people that work with the category network know this because the problem with the category network is it's community generated and it contains a lot of noise in terms of links and entities in the network. Let's see a couple of examples of noise we can find in the category network. One is the network as loops. For example, if we check the category government and we go up in the hierarchy by following the path public administration, public economy, economic policy, we reach again the same original category government. In our implementation, we used the algorithm described in this paper, a fast and effective heuristic for the feedback arc set problem. And basically, the feedback arc set problem, it's a way to organize the graph topologically based on the in and out degree of the edges. And once we have this graph sorted, we can remove the back edges to convert the network in a direct acyclic graph. A second problem with the network is not all the parent represent a taxonomic relation. To going back to the previous example, a French artist has a parent category called French art. And this is for sure not is a relation, because we cannot say an artist is an art. Even if the two concepts are related, you cannot include this in a taxonomical structure. This is a active research topic. There are many researchers that are trying to extract and infer taxonomies using the category network. The most recent works are MultiWibi and Ed Taxonomy. In both cases, they start from the English version of Wikipedia. They extract a taxonomy for English. In the case of MultiWibi, using two taxonomies, one for the pages and one for the categories. And in the case of head taxonomy, only based on the category network. But in both cases, they use linguistic feature to clean the network. Like in the case of head taxonomy, they used the heuristic, an heuristic based on plural to infer that the category is likely to be a taxonomic entity. These two approaches work quite well, but they have a different goal compared to what we want to do, because they have the goal to have a high precision taxonomy with a clean ontological structure. In our case, we are more interested in having a high recall on the category network, because in the case of sections recommendations, we want to generate recommendations based on the categories of the article. This means we want to maximize the number of recommendations we can generate from one article. For this reason, for our specific use case, it's more important to keep the original topology of the network and only remove what can add noise to our recommendation. So let's see how our method works in practice. Let's assume we have some generic high-level types for each article in Wikipedia. If you think about a taxonomic structure, articles in that are taxonomical should categories that are taxonomical should share the same types. For example, if we have the category scientist, what we expect is to have only articles about people. In our case, we used DBpedia to assign the label, the type to the articles, but we can use Wikipedia or other semantic knowledge bases. And in the case of DBpedia, we selected 55 top-level types that are the top level of the DBpedia hierarchy. And these types include people, organization, events, works. So very, very, very generic types. So now we can introduce the concept of purity. We can define a category as pure if the distribution of the types is homogeneous. Like in this case, on the left, we have the category and 5 articles of the same type. We can visualize this with this histogram, where we see we have 5 elements of type square in as part of this category. This is the case of scientist, where we have only people in the assigned article. The other possibility is a non-pure category on the right, and in the visualization we can see we have a distribution that is more heterogeneous, like the category football is not taxonomical, and in our case we define it not pure, because in football we have people because of player, we have events because of matches, and organization because it contains also teams. So the idea at this point is to run a bottom-up approach to clean the network by using this concept of purity, and remove the category where different concepts converge and create an impure category. This example, we have again football with football people, football venues, and football teams. The bottom part is composed by pure categories, and football is not pure. This is a real example taken from the real category network. So let's see in how in this algorithm works in detail. Imagine we have this small graph. Let's start with the leaf of the graph, like here, this category on the left bottom of the slide, and we can visualize the types distribution on this histogram, and we can see this is pure because we have only 3 articles of the same type. So we mark this as pure, and we go to the next category. Again, we have the same structure, same kind of distribution, and we can mark this as a pure. We can go up in the hierarchy, and we can check the distribution of the top category, the parent category, by considering all the articles in the subtree. Because if the ISA relation is respected, they must be of the same type. So again, we have here a pure category. This could be the case, for example, of football people, where we found pure category. Now let's move to the other leaf, and again we have a pure category, even if the distribution of types is based on a different type. This can be the case of football venues, where we have a pure category different from with a type different from football people. So now we can move up, and we reach the category that in the previous example was football, where we have a very heterogeneous distribution, and here we can mark this category as not pure. In this case, we can decide to remove the category. We can remove the edges. It depends on the application. This method is more like a framework to clean the category network. You can use it for different purposes and depends on the use case. Consider that if you remove the category, you are not disconnecting the graph, because typically in the category network, a category has multiple parents. For example, on the left side, we had football people. It's possible to have an additional parent that is sport people, that is pure, and we keep this subtree connected to the taxonomy. The problem is in the real world, there is no, it's not possible to have a perfect pure category because of the noise, and again, it's community generated, and some people can assign categories to articles even if they are not completely related. So for this reason, we are more interested to mark as pure the category with a high unbalanced distribution. Like in this case, we have visualization of this types distribution where we have a high prevalence of people, and we can assume this category is pure. To measure the unbalance of the distribution, we use the Gini coefficient. Gini coefficient is typically metric used in economic to measure the inequality of wealth in a country. And in our case, we want to measure the Gini coefficient of the distribution and set a threshold to decide when a category is pure and when is not. Like in this case, we have two examples. At the top histogram could represent, depending on the threshold, pure category, while at the bottom there is another distribution that is more heterogeneous, and if the Gini coefficient is below the threshold, could be marked as a not pure category. Now you are wondering how we can select the threshold. Again, this depends on your specific use case. In our case, for sections recommendations, we used a manually annotated dataset of 700 samples, where we annotated a set of transitive is-a relation, like a British scientist is a people, it's a person, yes, a positive example. And Gaelic game ground is a football, no, it's a negative example. We use a transitive expansion of the is-a relation to basically mark as a negative a path that should not exist in the taxonomy. And then we prune the network with different level, different threshold of the Gini coefficient. And we computed, using this annotated dataset, precision and recall. And based on this, we decided the best value to have a balanced set between precision and recall. In conclusion, we presented a language-independent framework to clean the category network. This is more a framework because it's a sort of parametric method, and you can customize it for your specific use case. For example, you can choose different types from different data sources. You can use Wikidata, you can use Wikipedia, or additional semantic knowledge bases. You can use a dynamic threshold. We didn't do it for our case, but you can, for example, choose a Gini coefficient, a threshold for the Gini coefficient based on the size of the category in terms of article or the depth in the category network. Because, for example, categories on the top of the hierarchy are more likely to receive noise from the bottom categories. An additional customization can be the way to select the threshold of the coefficient, the Gini coefficient. We use a manually annotated dataset, but potentially you can use a different method based on a different objective function. Like you can optimize the threshold for a specific use case using a validation set. And finally, you can decide to delete or remove edges, again, based on your use case, if you want to keep a super high recall or if you prefer precision. Again, I repeat again, this is a part of a bigger project about section recommendations. So if you are interested in more details, there is the link to stay updated, and thank you very much. If you have questions.
Thank you very much, Tiziano, for the presentation. I think we have a few minutes for questions. So I want to ask first Miriam, if there's anything that you can relay from IRC.
Sorry. Yeah, I think you're the first in the queue, Dario.
Oh, Emma. Ooh, how exciting. Yeah. Okay, so keep it short. And I was already familiar with his work, so really nice to see it presented in such a clear way. I have a question about something I've been thinking of for a while, that is about the robustness of categories as a function of who adds them. So I don't have any good data to cite here, but I imagine that in some cases it might be batch additions of categories at a large scale to an entire set of articles that maybe a single bot or a single user has performed just because they decided it was a good idea to add that category to thousands of articles. And conversely, I imagine there are articles where the addition of a category has been done more organically by a large set of users. And I was wondering if that could be used as signal that some categorization are more robust and some other types of organization are basically just like someone going bananas. Have you guys have any thought about something like this?
Yes, I mean, in our specific use case, we didn't find this problem. For the section recommendation, it was enough what I presented. Of course, you have to apply additional check on top of the Gini coefficient if you want to be more robust to these specific cases. Again, I present this more like a framework to clean the network, and you can plug different logic to manage specific use cases or specific, in this case, to clean this kind of noise.
That makes sense.
May I jump in here briefly? I think, Dario, this is a great point. It points also at a whole different research direction, namely basically building a taxonomy of of category usage? Like, what are even the use cases for which categories are used on Wikipedia? Because it's not only this kind of pseudo taxonomy, which is what we would ideally want, but people use taxonomies to organize their work. Like there are categories that are called stubs in stubs around universities or something like that. So that shows you that it's really a meta. There's this whole meta level, and characterizing what are the use cases and are they successful or not, I think would be super useful in order to understand whether the category system is already good or whether it should be redone or revised in any way.
Right. Yeah, I agree. There's a bit of like an edit persistence direction that could be applied to categories as well. Yeah, that makes a lot of sense. Cool. I want to open it up if there are other questions now. Miriam, anything from IRC?
Not for the moment.
Okay, so how about we're right at the half hour, so we can move on to the second presentation. Thanks, Tiziano. Stick around if you can until the end. The second presentation by Diego, and it's going to present. It's going to be a presentation about the second big part of this project around the section alignment. Diego, the stage is yours.
Can you see my screen? Yes. Okay, so hello everybody. Thank you for attending this talk. So today I will talk about aligning Wikipedia sections across multiple languages beyond the automatic translation, hopefully.
I'm sorry, I have to interrupt. Can you press present?
It's pressed.
We are not seeing it yet on the screen. There may be
okay, wait.
Okay.
What about now?
Just give a second. No, not yet.
Okay, let me stop sharing and share again. Share screen. Okay. Now?
Yes, now it's working. Thank you, Diego.
Okay, great. So I was saying I will present this work about aligning sections across multiple languages. This joint work with Baha, Bob, and Leila. And so the main idea of this part of the project is create a dataset with section names aligned across languages. So with alignment, we mean translation. Now I will explain the difference between translation and alignment. And why this is important? This has many different applications. In the context of this project, for sure, the most important is do cross-lingual section recommendations. So if we know something about an article that is in one language, and someone is writing an article in one language, this article is already in many other languages, we can use the sections there to recommend sections in the new language. And in general, for languages that we don't have too much information, as everybody knows, when you do recommender systems, having not too much data is a problem. So if we can connect all the languages, for every single language, we will have the knowledge from all Wikipedia. So that will be very useful. For sure, it's also useful for improve the content translation tool, and also in general, it's a good idea for general abstract ontology for section titles. So we can think later in sections as items more than just the title. And this has many applications for understanding better Wikipedia across languages. So what do we mean about alignment? So here, for example, you have 6 languages, and you have 2 section names or 2 section titles in each language. And what we want to learn is the mapping between this section. So, for example, here you will see that the ones that I can pronounce, premios in Spanish is the same that awards in English. I was learning how to say in Russian, but now I forgot. But you see it there in Russian and in Japanese and Farsi. And on the other side, you have the alignment between the biography, biografia in Russian, also in Japanese and Farsi. So you can say, okay, that's translation, no? So why not just to use automatic translation services? Can we trust in them? And anyone using sometimes, I don't know, any of the public translation tools that are available knows that they have some limitations. And they're far from perfect. They're usually good for understanding, but they don't produce excellent translations, like human-level translation. And also doing some tests from our specific use case, we found the accuracy depends a lot on the language. So for example, we test in English to Spanish and in English to Farsi, and the quality of the translations were very different. While English to Spanish was acceptable in many of the cases, in English to Farsi, the result was very different. But moreover, this is a bit different from translation because there are some constraints that we have or some challenge that we have where we want to, for example, keep the style and convention of each Wikipedia edition. So there are ways that people write sections that are not necessarily translations of others in different languages. And we want to keep that. We don't want one language dominating the style of the other languages. For example, in English, you will find that notes and reference are usually two sections, while in French, this is usually one section with these two things inside of that section. The other important thing is we want to give equal importance to all languages. So we don't want to use pivot languages, meaning that we don't want, for example, to translate to every language to English and then from English to the other languages. But we want to use all the information possible. So if we have information in 200 languages, we want to use that information to learn the mapping for the section for the language 201. And the other big challenge for this, basically considering these two things, is building the ground truth. So basically, given that we don't want to use a pivot language, we need to build a ground truth from having people that speaks all pairs of languages. So for example, we will need to find someone, if we want to use Latvian and Bengali, we'll need someone speaking these two languages with encyclopedia writing quality. But at the same time, we have these constraints and challenges, but we have also assets and opportunities. So we have this very active and committed community that is interested in these kind of things in Wikipedia. We have people self-reporting their language skills with the Babel template. I will explain in a minute. We have entity links across languages. So thanks to Wikidata, we can know that a page talking about global warming in Spanish is the same page in French, in Bengali, in Arab, etc. And the other good part is that given that many people use in NLP use Wikipedia data, we already have pre-trained models, a big set of different pre-trained models using Wikipedia across different languages. And particularly today, I will explain a bit how we use the Babylon project models. So let's start off what are we doing to building the training dataset. So I forgot to say this is a work in progress. So this is what we are doing exactly now. So the first thing that we did is try to build this training dataset, and we put some constraints, some things that we want to have in our dataset. So basically select a set of languages with different scripts. So not just Latin, but Cyrillic and Arabic and other scripts, and coming from different families, not just Indo-Europeans, but other families of languages. So in the right hand, you can see the languages. If you don't speak all these languages, maybe this is easier. So we will consider Modern Arabic, Russian, French, Spanish, English, and Japanese. So we will use this for learning how to do these mappings, and then we want to apply for all the others, for all the other languages. So even that we don't have someone speaking Latvian and Bengali, we will learn from here, and we will try to translate to transpose their with these pairs. So what is Wikipedia Babel? Wikipedia Babel is a template where people can self-report their language skills. So basically, they annotate from 0 to 5, with 5 being the most proficient and 0 being that you don't speak that language. So people can say which language they speak and in which level. So then we can go to the public information in the public service of query, and we can query there and get all the usernames and people that speaks that self-report that they speaks these languages. And surprisingly or not, in these 6 languages that we select, we find some overlap in all of them. So the most basic, so most of the people speak English, but we also find people speaking Arab and Japanese, or French to Russian, or French to Japanese, Japanese to Russian, etc. So these people is the one that we're contacting now through their user pages to ask to them for helping us to build this ground truth. This is what we are doing exactly now. Later on, I will give some pointers if you want to help us on that task. So exactly what is the problem definition? So basically having 2 sections, S1 and S2, where S1 and S2 are from different languages. We want to know whether S1 is the translation or the mapping of S2 across, and do this and repeat this across multiple languages. We can consider this as a link prediction task. So if you are familiarized with graphs, this will be a multi-part graph or k-party graph, which where each key group corresponds to a language. And the nodes are sections titles, and the links represent the translation or the mapping. Just a quick reminder, if you don't remember exactly what is a k-party graph, so k-part graphs are graphs whose vertices are or can be partitioned in 2 different independent sets. So the most usual, maybe you have heard, is bipartite graphs. So typical example of this is you have a graph where you have nodes that are actors and movies. And so you will have link between actors and movies, but not between movies or between actors. In our case, the key will be equal to the number of languages in our data set. For this training data will be equal to 6. And as you can see in the right, that would mean that we'll have mappings from one language to other, and not inside within the language. What are the features that we will consider for this? We will use automatic translation for sure. It's not perfect, but it's a strong signal that we can use. We will use the Levenstein distance, or also known as edit distance, that basically measures the difference between the different characters between 2 strings. This is especially useful for languages that are close, like Portuguese and Spanish, or Italian and Portuguese, or Dutch to German, etc. Also, we are planning to use the outcoming links within the sections, so basically where they are linking to. But the 2 things that I will explain today, they are the most innovative and interesting, I think. It's we will use word embeddings across different languages, and what we call the co-occurrence counts. So an embedding, what is an embedding? Maybe you heard about this. It has been kind of trendy in the last years in the NLP world. So basically, when you embed an object, it's taking a set from one domain and projecting another domain, preserving some structures that you are interested in. More specifically, a word embedding, it's when you take words and you project in a vectorial space. And in this vectorial space, the structure that you preserve is the semantic structure. So 2 words that are close in the vectorial space should be close semantically. Here I'm projecting use Disney. I'm projecting these section titles. Here you see in 2 dimensions, so this is what this algorithm Disney does, but in fact you are using vectors of 300 dimensions. And you can see that, for example, you have some clusters that are pretty clear that are related, like career and club career, or in the right top you see bibliography, filmography, discography, publications, works, gallery, or on the bottom you see awards and honors. So this is very useful. Usually it's done in one language, and it's what you use to measure. So you can then measure the distance between these 2 vectors, for example, using cosine similarity. And that will mean that if 2 words are close in the vectorial space, they are semantically close, semantically related. The point is that if you do this in multiple languages, usually the embeddings, what we're using in this case is fast text. Maybe you have heard about Word2Vec or Globe also. In this case, we're using fast text. If you learn in different languages, you won't get these characteristics because you won't have the words similar in the vectorial space. So here you see that just taking the cluster about bibliography and filmography, in the left you have the section titles in Spanish, and you see that both generate clusters, but they are not close between them. So here is where it comes into the play the Babylon project. This is people that basically is doing alignment between different vectorial space in different languages. What they do is a dictionary-based alignment across languages. So basically, they give information. They know that same points are the same. For example, using a dictionary or using nouns. And with this, they perform a linear transformation, and this allows to put in the same space both a pair of languages. So after applying this linear transformation, you can see that all the words are clustered. The cluster is not, the alignment is not perfect, as well as the embedding is always not perfect. But now we have a more clear sense of the sense of distance here gives more information about semantics. So this is one of the main things that we're using to understand that two things are translation. This plus the other, plus the automatic translation, and also what we call the concurrency counts. So basically, Wikidata allows us to align articles. We can know that an article is talking about a Wikidata item that can be a biography or can be any item in Wikidata, can be a place, whatever. So basically, we can align the table of contents of every single article in every single language, and if they exist in these two languages, we can count the concurrencies. So basically, we know that in the same article that usually appears personal life, appears primeros años in Spanish, or publications and works, or publications and publicaciones. So doing this concurrence counting, we also get good information about this alignment. So as I said, this is ongoing research. We are contacting people that we know that speaks one of these two of these 6 languages. So if you are one of these persons, please help us. Here you have the pointers. If you cannot remember now, please send us an email, and we will put in contact with you. You also have the fabricator task in the bottom. So this is about the mapping. But for doing a good mapping, we also need to understand synonyms. So within the same language, we know that there are 2 sections that means exactly the same or partially the same. And this is very important to know when you are doing the alignments, because this will help to do better alignments, and also to get a better understanding of this hierarchy of sections, of this graph of sections. So here is an interlanguage problem. So basically, having 2 languages from the same language, we want to know if S1 and S2 are synonyms. And one interesting thing that we understand here is that many times you have synonyms, like exactly the same meaning, but also many times what you have are partial synonyms. So 2 section titles that are usually used in similar ways, but they cover, they have an overlap, but they are not perfect translations. And for doing this, we are using again the embeddings. So the embeddings in one language that you already saw. Again, the edit distance. This is also very useful because many times, and it's related with the third feature that is a subset. So basically, many times you have one section that is overlapped with another one, even in the title. So education and background, it's overlapped with education or with background. So this is very useful also to understand when you have synonyms. But the feature that I want to explain you today is about what we call TF-IDF similarity. So basically, our intuition here is that two sections are likely to be synonyms if both tend to co-occur with similar sections, but they never co-occur among themselves, almost never co-occur among themselves. So basically, if you have, for example, background and education, they can co-occur, but it would be rare that they co-occur, but they will co-occur with similar sections. And the problem with applying this is that the most frequent sections tend to co-occur with almost all the sections. So, for example, reference, see also, and these kind of sections are present everywhere. So we need a way to remove this. And one way is to do with kind of a stop word removal. So basically have a blacklist. But the problem with this is first, there's some sections that are very frequent, but this is they're not equally distributed across all languages, and also that it's difficult to. We don't have a stop. This is stop words for every language that we're working with. So the solution that we developed for this was basically represent sections as TF-IDF vectors. So now you need to think as a section. If you know what TF-IDF is, you need to think on a section represented as a bag of sections, where the term frequency will be the number of co-occurrences of these sections with other section. And then we can apply the standard metric of cosine similarity between these two pairs of sections. And at the end, we can divide or filter somehow with the number of co-occurrency of these two sections. Yeah, basically that. We had got super good results with that. So here you can see some examples. This is just considering the TF-IDF similarity for sections that never co-occurs. So the co-occurrency here is 0 between them. So you can see that there are things that are very easy to get, but there are things like, for example, the last one, line up and band members, that it would be difficult even with the word embeddings, but the TF-IDF similarity works pretty good with that. Yeah, so as I told, we are working on this. We are now in the part of building the ground truth for both, for section alignment and synonyms. So if you don't speak both of the language, two or more of the languages that we're working with, but you speak one of them, you can help us with the synonyms. You can, again, refer to the link that I posted earlier. And if you speak more than one of these languages, it will be very helpful if you can help us labeling them. And we are testing different frameworks for the link prediction or link detection. And another thing that maybe it won't be part of this particular research, but it's something that for sure will be working in the future, is improve this word embedding. So now these word embeddings alignments are done based on a dictionary list, synonym list between these languages. But for sure, with information that we already have in Wikipedia, with especially with Wikidata, we can come up with a better way, more effective way to align embeddings across languages. And I think, yeah, you have some information there. And I think that's also, please, I'm happy to hear your questions.
Thanks very much for the presentation, Diego. And with that, we're going to open the room to questions, as well as anything coming up on IRC. Miriam, is there any question coming from the channel?
So we have a question from the YouTube channel from Dumisani, asking what language translation localization engine is used for this project.
So as I mentioned, we are not basing everything in a translation engine. The test we have done till now would be with Google Translate, also with Bing. But for the rest of the project, we are not tied with any of them, so we might use another another engines. I forgot now the name of the one that is used by the translation tool. That it's a different open source one that we might use for production as this.
Is it Yandex, Diego, or no?
I don't think so. I think we have something that different, but I don't remember exactly the name.
It strikes me that this work, aside from the use case that we're trying to solve here internally for the article recommendation, section recommendation problem, is a much broader problem. And I think a solution that you guys are designing and the data that we're collecting is going to be potentially useful for a much broader set of machine translation and NLP use cases beyond what we're doing here, right?
Yeah, absolutely. One comment on that. I think Diego mentioned this in his presentation. I think the key and focus here is not to get just the translation in a way that is understandable by the audience, but to get the level of translation which is encyclopedic. So this is kind of highly specialized translation for the case of an encyclopedia, which is really useful. I mean, that's kind of an addition to everything else that machines are considering. But the machine translation on the web is not done within context, right? So now we're saying refine and constrain yourself to Wikipedia.
Yeah.
What would be the translation?
Yeah, and it relates. I was thinking as you were presenting about a question that we hear in product a lot: is machine translation sufficient for creating stubs or adding to articles? And what is the reaction of the people who might read that from one language to another? So I think this could be some of it, I'm not sure exactly what parts, but could be very useful to the product department. So we might want to ask you about that.
I also see, sorry, just to jump in on another potential use case here is Wikidata descriptions, like labels and descriptions. I know this is a complex problem of how to map concepts Wikipedia articles to a variety of entities in Wikidata. But it strikes me that for some sections of Wikipedia articles that map to entities, this work could be really helpful to identify good candidates as descriptions or labels for these items. It's just me thinking aloud. But I see Wikidata could also benefit significantly from this work, I think.
Yeah, for sure. I think section translation, so section titles usually had a lot of semantic power, let's say, no? If we are able to do this, maybe labels from different types will be easier, and then anything that we can do after this works. The concept of alignment is very interesting for any cross-lingual work that we do in the future.
I have a question about, I think you mentioned that in some cases there's not a one-to-one correspondence between languages. There are some section titles which might mean for what we have two different things in the other language. And I'm not sure, I think later maybe you'll be able to finish out this project, but a year ago we had an intern who worked on just counting the most frequent section titles, and she had some observations like this, like I think one example was war C on the French Wikipedia. It's C also, but it's also external links. So they both put internal and external links. And I think that's also with literature, bibliography, notes, references, there's a lot of different approaches. And how is that mapped in this framework? Or can you recommend two different section titles as translation of one section in another language? Or?
Yeah, so this will be one of the goals. So knowing that, because if you have two sections mapping to one section, so let's say the example with French, you have two sections, and in French is one section. If we also know that these two sections are not synonyms in English, so we know that notes and reference are not the same thing, and they map to both map to one section in French, that would mean that basically this section is representing two different things in the other language. So it's something that we are considering. So basically the synonym detection part is for helping also in that. If we know that two things are synonyms, we can collapse them in one node, and then we can select one of them by different things. Popularity might be one, but maybe there are others. But if we know that they are not likely to be synonyms, this will help for this not one-to-one translation recommendation. 1-to-N.
We have another question from YouTube about, are there any plans to represent languages not supported in Google Translate, mostly African languages?
Yeah, for sure. As I said, the translation, we're not just using Google, and the automatic translation is one of the features that we are using, but not necessarily the main one. We already have what they did with the Babylon project. I think they have around 90 different languages listed there. But given that this is based on fast text, so basically, and it's a open source project, we can align to any embedding where we have information. So basically, if we have a Wikipedia in one language, we can create embeddings for that language, and then we can easily, and when I mean easily, it's really easily align with the other languages. For sure, for languages that we don't have too much content, too much, in this case, pages, the quality will be lower than in very populated Wikipedias. But for sure would be better than nothing, and for sure could be useful for do the recommendation of the most popular sections.
I think that's all from these channels. Thank you, Diego.
Cool. Can I make one remark? Yeah, so basically, I want to start with the first part of the presentation. I think Tiziano started working on the project of what we call cleaning up the category network with all the caveats that he talked about in September 2016. And we have been meeting basically every week and discussing this project since then. And there were weeks that we just left after the meeting, and I was not sure if Tiziano is going to come back the next week. Like, I just want to say that he has done an incredible amount of work and has worked on one of the hairiest problems that Bob, Michele, and I have seen in our research career. And it's amazing to see this coming to this level. And I'm really looking forward to doing the data releases that we have been discussing associated with basically like empowering others to use what you have brought this project to, Tiziano. We have been discussing, blog posts and like how to use this as a community, as a feedback to the work that the community has been doing on potentially cleaning up parts of the category network with the caveats that Bob mentioned. So thank you for all of that work to the three of you, but Tiziano, you specifically, you did a lot of heavy lifting over the past year and a half. And of course, to Diego, Bob, and Baha, right? I mean, this is a project that we started in the past, I think 6 months ago, and it's been moving fast, and it's really exciting area. It's I attended Wiki Indaba remotely over the weekend, and as Dumi and others have brought up in YouTube, there's a lot of discussions about what is our role in the smaller languages, right? And what do we do if the internet or web is not supporting these small languages? And the work that we're doing in this space is critical to basically empower users, editors, readers in these languages to have access to the content. So let's just push as much as we can in this space and get the results, data, everything out. Thanks for everything you do.
Yeah, here. I also want to ask Michele and Bob if there are any additional questions or comments. Now we have an opportunity to have you here. Sorry if I'm calling you out like this.
Oh, yeah, can you help me soothe my daughter?
Sure.
That's the most pressing one.
Yeah, I think we'll pass with Bob.
Yeah, no, one thing that I want to mention about the language that are not well represented in Wikipedia is that this is the quality of word embeddings improves with the amount of text. So I hope that instead of, if we can produce medium quality, let's say, recommendations in these small languages, I hope that this will help people to write more, and while they write more, the word embeddings will improve, and with this improvement, the alignment will be better, and we will produce better recommendations. So I think it's very important to work in this kind of spaces, because I think it can break the inertia of some. So this happens with everything. It's kind of a networks effect, but even with some thousands of articles, we can start working with embedding. So I think we can work on this with almost all the projects in Wikipedia. So I think it's a good starting point.
Yeah, and I also want to say I just retweeted the call for participation in the labeling campaigns. Obviously, if you want to be able to cover all languages, including like underrepresented languages, really critical that we get multilingual speakers to help us out. So please, if you're watching this and if you want to help, check the links that you'll find in the presentation or on Twitter or on the research list. Sweet. Anything else, Miriam, from the channel? Or from the room?
Not really. No, I think we're good.
All right. So I think we're going to wrap it up. Thanks, everybody, for joining. Thanks to our speakers, Diego and Tiziano, and everybody else who joined us here in IRC and on YouTube, of course. And we'll see you all next month in April, the next showcase.
Hey, thanks everyone.